And I'm going to start sharing as well. Oh, here is the syllabus. So we are right here. We did rotational kinematics. There is just one more thing I'm gonna introduce to you. Okay, it's very simple. There's not much difficult. It's not very difficult, so you'll be able to memorize that regarding rotational kinematics. Okay, and we are doing rotational dynamics. There won't be time to do the other thing, so we'll update it soon. And the day after tomorrow, we have an exam number 3. Okay, on Wednesday. Falling behind, we have, my goodness, we have only 2 more meetings to go. Okay, and let's see if we can speed things up and get ahead of the schedule here. All right. Let's go for the ego. Yeah, here you go. Chapter 8, right? We're gonna cover this one. It's very simple. It's not very difficult. Okay, rotational kinematics. Chapter 8, rotational kinematics. Going back to the syllabus, let me highlight today's date. Okay, and we already did that. Let's see if we can do this other 2 chapters here. It's gonna be a little tough, challenging, but let's see what we can do. Okay, so vector nature of angular variables. Okay, by the same token that we have, by the same token that the linear parameters are vectors. Okay, so let's see. There's a we're doing a review for the upcoming exam. Yeah, let's see if we can do at the end. Okay, I want to get ahead of this material here, and then let's say an hour before the exam, an hour before the class ends, we do the review. Okay, remind me around 11 a.m. please. So here you go. But same token that the linear parameters are vectors. Okay, that many of the linear parameters are vectors. Comma. So are the angular parameters. The first one you have to know. The first one you have to know is the angular velocity. Okay. And you must know is the angular velocity. The direction of the angular velocity is very simple. The direction of the angular velocity is very simple. It's very simple to obtain. It is given by the right-hand rule. I'm going to spell out the right-hand rule here. Okay, you use the palm of your right hand. You move, let's say you move the palm of your, don't forget, right hand. You move the palm in the direction of rotation of the object, and the thumb points in the direction of the angular velocity vector. Okay, so there is some illustration here that I'm going to show you. This one right in here. Okay, well, let's start with this one, right? Here you go. That's the axis of rotation. Okay, that's the axis of rotation. The the displacement here. Let's see if I can get format shape line. Okay, so here we go. I'm gonna put. I'll use this one, and okay, I put in the wrong direction. See the arrow here? I put in the wrong direction. Let's put in the right direction. This one. Now we cannot see the direction, but we will be able to see it soon. All I have to do is to change the fill. Yeah, here you go. See the little arrow right in here, right? It's that small, right? Let's see if I can make it larger. Yeah. So the object is rotating like that. Okay, and that's the other one right here. Fill, no fill, okay? So you can see the head of the arrow. So all you have to do, is orient your palm. Take a look at the palm of my hand here. In the direction of rotation. The object is rotating this direction. Don't forget it's the right hand, right? So the palm moves in the direction of rotation. The thumb points in the direction of the rotation. Looking from the top, right in here. Okay, now the palm of the hand is going to be oriented in a different way, right? The palm of the hand rotates in the counterclockwise direction. The arrow, the direction of the vector velocity, angular velocity, is towards you, okay? Towards coming out of the plane of my screen, okay? So that's a simple rule. You will need this rule later on, so make sure you memorize it. So the right hand rule applies to the to the vectors to the vector of angular velocity, applies also to the x, y, z, the direction of the x, y, z axis, and so on. So you're going to be using that over and over again. Okay. The other vector you have to know. The other vector you have to know is the angular acceleration vector. Okay. Its direction depends on the direction of the angular acceleration. Depends doesn't mean it's the same, right? It depends, okay? You want to emphasize it here. It doesn't mean it's the same. Okay. On the direction of the on the angular velocity. Oh, here you go. So in order to find the direction of the angular acceleration, you have to know the direction of the angular velocity first. So in order to know the direction of the angular acceleration vector, first you must know the direction of the angular velocity vector. Okay? And there's a very simple rule here. The direction of the angular acceleration depends on whether the object is accelerating or decelerating. If the object is accelerating, magnitude of omega is increasing, okay? The angular acceleration points in the same direction as the angular velocity. The angular acceleration vector points in the same direction as the angular velocity vector. On the other hand, if the object is decelerating, magnitude of omega is decreasing, the angular acceleration points in the opposite direction of the angular velocity vector. Okay? So that's simple. Okay? Units of angular velocity. There are radians per second, degrees per second, rotations per second, RPM, rotation per minute, RPM, right? RPM is what your tachometer measures for the rotation of your engine in your car. And then you also have RPS, rotations per second, where one rotation corresponds to 2 pi radians, right? 2 pi radians, which is equal to 360 degrees. That's what you have to know about this last section in the book. Okay? And now we can start talking about rotational dynamics. Rotational dynamics. This is a more challenging chapter than the previous one. Because we introduce concepts that are more involved. Okay? So you already know that for every linear kinematic quantity, there is a corresponding angular counterpart. Okay? Linear position as, linear position, then the counterpart of linear position, its counterpart is angular position. Linear position, comma, angular position. Linear velocity, the counterpart is angular velocity. Linear velocity, angular velocity. Linear acceleration, angular acceleration. Okay. And now you have to think in terms of the other linear parameters. What about the other linear parameters? Such as, you want to list it here. First one is the linear force. Linear force. What about the linear mass? Okay. What about Newton's first and second laws? Do we have an angular correspondence? Okay. What about, I'm emphasizing, linear kinetic energy. Do we have an angular counterpart? What about the other linear parameters? Do they also have an angular counterpart? Okay. Linear force, linear mass, Newton's first and second law. And then, oh, before linear and kinetic energy, right? We must have linear work, okay? Before we talk about the kinetic energy, we have to talk about the work to have a corresponding angular work, okay? And then we also have the work kinetic energy theorem. We have a corresponding angular work kinetic energy theorem. And finally, linear momentum. Linear momentum. The answer is yes. The answer is yes. We do have, but they have different names and different mathematical definitions. Just like we had different mathematical definitions for angular position and angular velocity. Different mathematical definitions. Okay? Let's start with the angular force. Let's start with the angular force. This angle, which is called torque. Okay? It's called torque. There is a very simple way of illustrating the torque. There is a very simple way of illustrating the torque using our day-to-day experience. Okay? So let's go here, and I'm going to consider the door at your home, okay? Here we have the door that is a rigid object, a rigid body, and it has an axis of rotation that passes through the hinges of the door. Okay, put a nicer axis here. Here you go, here's the axis of rotation of my door, right? Looking from the top, that's how you see. You see the axis of rotation here, and you see the rigid body right in here. Okay? You can apply different forces along the length of the rigid body. Let's do the movie again. Let's do the movie again here. I will erase that stuff. Okay. Consider a door with the hinges. Let's do that without the hinges first. Door. This one goes here. Well, consider a door. Consider a door, which is a rigid body. Okay. The door, rigid body. A door with hinges. With hinges. Let's put it here. 1, 2, 3, right? With hinges. Its axis of rotation. Its axis of rotation passes through the hinges, right? And that's where I start illustrating the axis of rotation here. The door can open or close, can rotate about this axis. and rotate. Let's get another illustration here so you can see it better. Let's see, right? I want this one. Oh. I want this one right in here. Yeah, this one right in here. Huh? Can you picture that? Right? Can rotate about this axis. You can go in both directions, right? Either in this pointing to the right or pointing to the or the other direction, right? Either clockwise or counterclockwise. That's what this door can do. Of rotation. Like that. But looking from the top, right? Looking from the top, we have the axis of rotation and the door. Looking from the top of the door. Looking from the top of the door. Door and axis of rotation. Okay? The door can rotate in either direction. Here you go. Can rotate in this direction. Oh, I don't like that. Let's see here. Let's see. I'm gonna do this my own. I don't like that. Let's see. Oops. Oop. What's going on here? Yeah. Yeah. Okay, you got it. You go. The door can rotate in this direction. Right? Or the door can rotate in the other direction. Right? You got it? I'm gonna make this one like that. No fill. Bring it to the top. Bring to front. No, I gotta do more than that. White field. Okay, now we have it. And I'm gonna substitute this axis of rotation by the other. Okay. If the door rotates in the counterclockwise direction, it is as though as the axis of rotation is pointing towards us, toward us. And this direction is represented by a point. Like that. Let's see. Oops. No, this is not what I want. I want the other one here. This one here. Right? A smaller circle with a black fill to illustrate the point of the arrow. Point of the arrow. Okay, like that. Like that. Here, point of the arrow. Now you do the right hand direction in the second figure, right? And then we illustrate a cross. That this cross is an illustration of the back of the arrow. Like that. Here you go. This cross here. Illustrating the back of the arrow. The direction of the angular velocity vector. Like that. Okay? But let's go back to our dynamic angular force, right? Let's go back to our angular force. Here you go, going back here. We don't need that anymore. Here you go, I'm not gonna need that either. In order to define an angular force, we have to exert a force on this door, okay? Force in this direction, the door is gonna rotate in the counterclockwise direction, okay? But illustrating the force is not enough. Illustrating the force is not enough, okay? Because this, this force is gonna make this door, is gonna impinge an angular acceleration to this door. Do you see that? But the angular acceleration is going to be different whether the force is here or anywhere along the door, okay? So in order to quantify this angular force, we must also illustrate the vector position of the point of application of this force, okay? Here you go. And that's what I call R. Like that. Your force is being applied somewhere around here, right? Here you go. In the door. And you have this vector position of the point of application of the force. Let's just position that, like that. And I don't need that anymore, right? Point of application, okay? So let's write that down. Okay. Okay. So if a force is being applied, okay, let's say, if a force, let's write it this way. If a force F is being applied to a rigid body, then the rigid body may rotate about a fixed axis. Okay? The point of application is, so consider that the point of application of this force with respect to the axis, of the rigid body is located distance, r, from the axis of rotation. With those two, with these two parameters, we can define the angular force or torque as follows. Okay, so here you go. Torque is represented by the Greek letter tau. Okay, is the point of application of the force itself, and the angle between those two vectors. Okay? In the above theta is the angle between the two vectors R and F. Even better, I'm gonna put in vectorial notation, okay? So there is no doubt about those parameters are vectors. But then I have to do something else. You cannot have a multiplication between two vectors, right? So what I have to do. I have to put a magnitude in there just to emphasize that those two parameters are vectors. And then here go. In the above, comma, theta is the angle between the two vectors R and F, right? R and F. R and F when their tails are touching each other. Okay? Their tails are touching each other. So just to illustrate here, right? So if this one is the vector force and this one is the vector position, right? Of the point of application of the force, what do we have to do? The angle theta is going to be the angle when you place those two vectors, tail to tail. And here, I'm going to illustrate this angle theta, right? Q symbol. Like that. So let me make another slide here so you don't so you don't miss no, that's not what I want. I want this one right in here. You go. Vector position of the point of application of the force. This R, I'm gonna move here to the right. And this R must be moved to the back. Don't forget, those are vectors, okay? In this specific example, the two vectors are 90 degrees of each other, right? But we can have other force orientation for the force. We can also have a torque in which the forces makes this angle here with the vector position. That's another example. And the definition of torque is not going to change. It's still going to be Rf sine of theta. Okay? It's still going to be Rf sine of theta. Okay, having said that, now we can look at the properties of this vectorial force. Okay? We can look at the properties of this vectorial force. Which type of property? Okay, if you apply the torque right here at this position, you're going to have one torque. Okay? But what if you apply the same force at a larger distance from the axis of rotation? You're going to have a different torque. Okay? I'm going to do like that. Here you go. Here, we are going to have torque 1. I'm going to put, I'm going to put the subscript 1 to differentiate it. Subscript like that. Okay, and someone is trying to get in. Okay, here we're gonna have one torque, and I'm going to emphasize that this is gonna be, F1, and this one gonna be R1, right? This torque is going to be given by one, F1. And I'm gonna change because vai ter que maybe, yeah, and subscript. Since angle theta is 90 degrees, we do not have the sign there, right? Here we also have F1 because the force didn't change direction nor magnitude. Okay, but we have instead R1. Instead of R1, we're going to have R2 here, right? And consequently, we are going to have a different value for the torque. It's going to be R2 F1. A different value for the torque is going to be torque number 2, which, by the way, I know for a fact. Because R2 is greater than R1, I know that this torque number 2 is going to be greater than torque number 1. Like that. Make sense? Right? Like that. Mhm. Now, suppose that we have the same magnitude, but now you have a different angle for the force. Okay, I'm gonna put that here. R2 is here. The magnitude here is the same, but the force angle, the angle that the force makes is different. I will duplicate this vector so I can get exactly the same length for the vector, and I'm going to rotate it. Format shape, here you go. Position, rotation, let's go. Yeah, here you go, I'm rotating. I'm rotating this vector that has the same length as the vector force F1, okay? And let me get rid of this guy because it's not realistic. What I want to say, right? Is here you go. Here's the angle. The magnitude is the same. But the force is different because it has a different angle. I'm going to put F2 here. Now we're going to have a torque 3 that's going to be given by R2, F2, sine of theta. Okay, which is equal, yes, which is going to be, and this one's supposed to be tau 3, right? Which is going to be, I don't need that. Which is going to be less than tau 2, torque 2. Okay. Okay, what we have here, we have that magnitude of F2 is the same as magnitude of F1, like that. And I got to get this thing here adjusted properly. Here you go. But then I gotta put the magnitude here. Not this one. Let's see. Yeah, this one. That's good. Yeah, magnitude. Like that. Magnitude of F1 is equal to magnitude of F2. Okay? But the torque is still less because it has an angle here. Okay? So, in practice, you notice exactly that, right? If you apply a force to your door here in the middle, you have it's more difficult to make the door rotate than if you apply a force right in here. That's because your torque ends up being greater in this case. The force is the same, but the torque ends up being greater because you're applying the force at different points. Okay? And the same thing here. If you apply this force at an angle, okay, the force is going to be, the torque is going to be less than you have to apply the force at a 90-degree angle. Okay? To maximize from the above equation, it's clear that in order to maximize the torque, the force must be applied at an angle of 90 degrees with respect to the point, the vector point of application of the force. Okay? And the magnitude, and magnitude of R, and magnitude of R must be the largest possible one. Okay? That's how you maximize the torque. That's how you maximize the angular force. Okay? If okay, what about the sign of the torque, right? A torque can be either positive or negative. Okay? If the torque is applied in a direction that makes the door rotate in a counterclockwise direction, okay, I'm gonna put the torque will be positive. Otherwise, the torque is negative. Okay? So here you go. Here, the torque is positive because it's making the door rotate in the counterclockwise direction. Let's get another one. Counterclockwise direction. Counterclockwise. Counterclockwise. Torque. Counterclockwise, comma. Positive torque. counterclockwise again. Positive torque. Counterclockwise rotation, right? Let's put it this way. Positive torque. Counterclockwise rotation. Positive torque again. And here, clockwise rotation. Negative torque. Negative torque. Let's get this thing here centralized so it looks nicer. Those are the things you have to know. Okay, units of torque. Let's take a look at the units of torque. The units from the above mathematical definition, comma, the unit of torque is, here you go, like that. Unit of torque, you go, square bracket is the unit of R, the unit of force, and the unit of the sine of theta. Like that, right? The unit of R, you already know, is the meter. The unit of force, you already know, is the Newton. The unit of the sine has no unit whatsoever, so you write that as 1, right? And that's the unit that ended up being the torque, Newton meter. By the way, it's the same Newton, it is the same unit of work, right? But we don't label it as joules because torque is not energy, right? It's not work. It's just torque. And the fact that it has the same unit as energy is just coincidence. And the fact that it has the same unit of energy is just coincidence. They're both different concepts. They are both different concepts with the same unit. 940. Okay. Right, just like the definition of work, right? Here you go. The definition of work or energy in general, okay? Here you go. Force is here. Force is here. You know, displacement is here, which has a unit of meter, and position is here, which also have a unit of meter. But look here at this term. This term is cosine. The other is a sine. Can you remember that? Okay. So put them side by side, right? Put them side by side. Here you go. Putting them is the same unit, them side by side, right? We have that. Now that we defined, the angular force, we can look at the other consequences such as the such as Newton's first law, right? Remember that if if net force is equal to 0, it implies that an object will be either at rest or moving with constant velocity, right? And by the way, the same apply to net torque. If the net torque is equal to 0, comma, here you go, I'm going to erase that, the rigid body will be either at rest, right? Omega equal to 0, or rotating with constant angular velocity. More students coming here, okay? Okay. For a reason, we say that when the net force is equal to 0 and the net torque is equal to 0, we say that the rigid body is in equilibrium. Okay? When the net force is simultaneously, okay? You must have this simultaneous condition. We may have a net torque equal to 0, okay? Please note that we may have a net force equal to 0, but the net torque may not be necessarily equal to 0, okay? Very important. Let me see if I have a example here of a net force equal to 0, net torque different of 0. Let's see here. Oh, right in here. Okay, here you go. I'm gonna take it out. Put that at the top. Here you go. Two forces being applied to this rigid body. What you see here is the point of or the vector point of application of the force. Okay, one force is applied here, the other force is applied there. Here, the object, the net torque is going to be 0 because this force here is making the object rotate in the clockwise direction, whereas this force is making the object rotate in the counterclockwise direction, and they're going to cancel each other. Okay? So I'm going to copy that and put in the snipping tool. Let's go get my snipping tool. Okay. It's rotational equilibrium, but it's not in translational equilibrium. The object is going to accelerate in this case. Okay. Example of an object. Example of a rigid body in rotational equilibrium, but not in translational equilibrium. So this rigid body, consequently, this rigid body is not in equilibrium. Let's put in net equilibrium, right? Let's put that in net equilibrium. Let's put it this way. And I'm going to, that is the other situation, right? Here you go. Net force equal to 0. Okay. And net torque is equal to 0 in this case. In this case, this force is producing a counterclockwise torque, and this other force is producing a clockwise torque. Object under rotation and translational equilibrium. Okay, that's net equilibrium. That's in net equilibrium. Let's put it here. Example. And we are going to show another one. Yeah, object under. Example of a rigid body simultaneously in rotational and translational equilibrium. Yes, I'm gonna put it net equilibrium. And there's the other way, there's the other one too, right? Here is in rotational equilibrium, but not in translational equilibrium. And we have this other possibility that the object can be in translational equilibrium, but not in rotational equilibrium. Can you picture that in your mind? Okay, there is one more picture here that I can put it here for you. All right, try to picture in your mind an object that are in translational equilibrium, but not in rotational equilibrium. I can use exactly the same figure. Okay, what I have to do here, I have to change the direction of my force. Okay, and apply it at a different spot right in here. My vector position R is going to be here. Okay, and let's put this F right here at the top. I'm going to put here, this one is going to be my R1, right? Subscript. Subscript. And this one is going to be an R2, vector R2. Their magnitudes are the same. I'm going to change their colors. Here you go. To make it easier to identify, right? Here you go. This other one too. And let's make this arrow red as well. Right? Like that. And I can object under rotational, under translational equilibrium. Translational equilibrium, but not in rotational equilibrium. And let's get this one here and place there in the notes. I'm gonna put it before the other one. Like that. Example of a rigid body in translational equilibrium. In translational equilibrium, but not in rotational equilibrium, right? Clockwise rotation, clockwise rotation for this force, clockwise rotation for this other force. So there, the torques are adding up, but the forces are subtracting each other. Consequently, this object is just gonna be rotating either a single point or moving with constant velocity, right? So 3 important examples. So you can have an idea of how the torque works, how this angular force works. Okay, so let's I'm gonna copy and paste a table with the angular parameters so far that we have. Okay, so here you go. Linear and angular, right? Position, displacement, average velocity, instantaneous velocity, average acceleration. You know, angular position, angular displacement, angular velocity, instantaneous angular velocity, angular acceleration, instantaneous angular acceleration. And now we have these two new concepts that you see right in here. Okay. Net equilibrium. In order to have net equilibrium for a rigid body, in order to have a net equilibrium for a point particle, right, the net force in the particle must be zero. But for a rigid body, it's a little bit more stringent, the condition. You don't, you not only must have a net force equal to zero, but simultaneously you must have a net torque as well. Okay. It's 9:53 right now. We have 13 students here. Let's take attendance. Today is the 25th. Audrey Aguilar. See, are you there, Audrey? Okay, I'm gonna put a star here for Audrey. Brianna Carrillo. Yes, thank you, Brianna. Jazzy Castellano. I don't see Jazzy here. Next is going to be Gabriel Contreras. Let's see, no Gabriel Contreras. Next is going to be Molly. Molly's here, right? Thank you, Molly. Brianna Carrillo, yeah, right in here. Henry Kim. Thank you, Henry. Ruth. I don't see Ruth. Mandujano. Let's go to zero here. Noemi Martinez. I don't see Noemi. Danae Miller.
I'm here.
Thank you. Henry Kim. Okay, Ramon Olivares.
Here.
Thank you, Ramon. Taylor Ford. I don't see Taylor. Stephanie Ramos. I don't see Stephanie here either. Next, Jeremiah. Thank you, Jeremiah. Sha Rosario. I don't see Sha. Ali Standard. Hello, Ali. Okay, I'm gonna put a star for Ali so far. Jason Strait.
Here.
Ali, okay, Ali. Thank you, Ali. And Jason is here. Elena Trujillo. I see Elena Trujillo in my roster. I'm gonna give her opportunity to reply. Okay, let's put a star here first. Jason Valadares.
Here.
Thank you, Jason. Laurel Williams. Thank you, Laurel. And Nuhamin Wandimu. No, Nuhamin here. Alia Zavala. Are you there, Alia? Let's give her a star and let's see how many. 10 on 11, 12, 13, and it matches how many I have there. Okay, so let's take our break now. Break 9:56 a.m. to 9:11 a.m., right? And Elena has answered me. Let's see, Elena Trujillo, right? Anything else? Anybody else? So Audrey, are you there, Audrey? And Alia. Okay, so let's have our break. Now it's 9:57, just one more minute, right? And we meet again at 9:12. See you in the next 15 minutes. I'm back here. Okay, Alia, thank you for the message. I already gave attendance. And what about Audrey? Audrey, are you there? Looks like Audrey left. Okay. So let's see. Let's see. Chapters for the exam is chapters 5, 6, and 7, right? So chapters 9, 8, and 9 are not going to show up in this exam, but it's going to show up in the final. And let's go for another 45 minutes. And then we do a quick review of the material. Let's see here. 2023, 2024. Am I sharing the screen? Yes, I am sharing the screen. Here are what we have covered so far of chapter 9. Okay. Action of forces and torques, rigid body in equilibrium. And don't forget, in order for a rigid body to be in equilibrium, those two conditions must be satisfied simultaneously. And I mentioned, let's review here those three, right? So here you go. We have 3 cases. We have 3 important cases. 2 of them is not an equilibrium of rigid bodies of a rigid body, right? So the first one that you see in the illustration, right? Net torque equal to 0, but net force different of 0. This is not net equilibrium. No net equilibrium. No net equilibrium, right? In this case, the rigid body does not rotate. It is in rotational equilibrium. But it accelerates, not in translational equilibrium. Okay? Another student coming in. In the second case, the middle one, right? That's the one here that the rigid body is accelerated to the right, but it's not rotating. Here you go. Here's the case that the rigid body can be either at rest or moving with constant velocity. Okay, net force equal to 0, but net torque different of 0. Okay, no net equilibrium. In this case, the rigid body is either, let's say the center of the body, the center, in this case, let's put it this way, the center of the rigid body, we also call it the center of mass. The center of mass of the rigid body is either at rest or moving with constant velocity. Okay. And in the case of this example right here, the center of mass coincides with the geometrical center of the rigid body, okay? So this point right in here is either at rest or moving with constant velocity. Okay. But the object, the rigid body, not the object, the rigid body has an angular acceleration. Okay. And I gotta put here translational equilibrium. Yes. No rotational equilibrium. No. And finally, the third case, net force is equal, net force and net torque are equal to zero. Equal to zero. Its forces must be applied at a specific places on the rigid body, which has a center of mass that is either at rest or moving with constant velocity, right? And on the top of that, and on the top of that, and on the top of that, that either it does not rotate or rotates with constant angular velocity. Right? So those are the cases here. Let's do example 3 in the book. Let's take a look here at the book. This is the book, example 1, example 2, example 3. No, is that example 3? No. Let's see. Example 3. That's this one right in here. Okay. A woman whose weight is 530 newtons is poised at the right end of a diving board with a length of 3.9 meters. The board has a negligible weight and is bolted down at the left end, here, right in here, while being supported 1.4 meters away by a fulcrum, as in figure 9.5a. Show that find the force F1 and F2 that the bolt and fulcrum respectively exert on the board, okay? We can solve that doing free body diagrams. And don't forget this board here, you must assume that this board is a rigid body. Did he say that? Yeah, he didn't say that. Okay, very important. You must assume that this board here does not flex, okay? But it is a rigid body. He didn't say that, but that's what he means. Okay, example 3. Let's I'm gonna add this important piece of information. Example 3 in the book. Board, rigid board, okay? Rigid board, fulcrum, bolt, and diver, right? Like that. We're gonna come up with a a drawing here. Let's see if I already have a drawing here. If I don't have, I'll have to do that from scratch. Yeah, I'll have to do that from scratch. I'm gonna take advantage of this drawing here. Right in here. I don't want that. I'll do that from scratch. Board. Here you go. Thickness of the board here. The line. Well, I like to make thicker lines. Let's see. Yeah. So it's very visible. I'm gonna make a line here to indicate the floor, like that. Let's make sure my line is properly positioned. No, it's a little bit. Yep, right now, as you go, we have a bolt here on this end of the board. All right. I'm gonna send that to the back to give the illusion that it's a bolt that bolts our plank. We have a fulcrum. Make it thicker. Yeah, make it thicker so it looks nicer. And make this one thicker as well. All right. And then we have the diver at the end right here. Okay, that's what we have here. And then I can erase my grid lines. Going back to the enunciate, right? A woman whose weight is poised at the right end of the diver with a length 3.9 meters. Okay, the board has negligible weight and is bolted down at the left end while being supported 1.4 meters away by a fulcrum. Okay, 530 newtons, 3.9, 1.4, right? 5, those are the numbers. 530, 3.9 lengths, 1.4 meters away. Rigid board. Here you go. Rigid board. What, 3.4 meters? Let's make sure that's right, huh? No, 3.9 meters. 3.9 meters long. And negligible mass. Right? Diver has a weight, 530 newtons, around 53 kilograms. On the extreme right of the board, bolt on the extreme left of the board, fulcrum 1 point, how many meters again? You don't rely on your 1.4 meter. Don't rely in your memory, right? If you're not sure, just go back, even if it takes longer. Okay. And he's asking. And don't forget, he should have also said that the board is in net equilibrium, right? Let's make sure it's net. Yeah, it's in net equilibrium. He didn't say in the enunciate, right? But he's using this condition here of net equilibrium. Okay, he was supposed to have said document those two things. Okay, one, he was supposed to say that the board is a rigid body, doesn't flex, and two, the board is supposed to be in net equilibrium. Okay, so going back to our, here we go. We gotta come up with our free body diagram. Mass of the board is negligible, consequently, the weight of the board is negligible as well. So we don't have to worry about this force, but we do have to worry about the force that the diver applies to the board right here at the edge. And this force is going to cause a torque in the clockwise direction, okay? Oh, begin arrow, okay. Format shape, size, and position. Must be this one here. Let's see what's going on. That's the arrow. No line. That's this one here. Here you go. Thicker, right? That's the weight of the woman. Let's say I'm gonna call it W. The force here is W. This fulcrum is applying an upward force. Let's say this upward force here. Right? Since this weight is making the board rotate in the clockwise direction, this bolt here must prevent the clockwise rotation, right? In order to prevent the clockwise rotation, the bolt must apply a downward force to the board, which will counter the clockwise rotation of this weight. So that's our free body diagram. Three forces. The weight of the board is not showing here because the enunciate told us that the mass of the board is negligible. And going back here, let's see, he's asking, find the force F1 that the bolt and the fulcrum respectively exert on the board, okay? So here you go, bolt, here is F1 on the left side. And here is F2. And here is F2 on the middle of the board. I want all those forces to be black in color. See, bring to the front, right here. Okay, so that Those are the forces that we have. So free body diagram for a rigid body. This is a free body diagram for a rigid body. Like that. Solution. Find the forces at the bolt and the fulcrum. Okay. Solution. So the solution starts with the drawing. Start with the drawing right in here. You know, board in equilibrium. Right? What does it mean? Board in equilibrium. I can copy what I have here. Net force is equal to 0. Net torque is equal to 0. I want to put the net force equal to 0 at the top because it's a more familiar concept, right? Okay, so here goes net force. So we can write down like F net is going to be what? F2 minus F1, minus F1 minus W equal to 0. We do not know F1, we do not know F2. I'm assuming that the force of 1 is downwards, right? Let's see if he put downwards the force as well. Yeah, he put down as well. Yeah. Okay. And then we have net torque. Net torque is equal to 0. So net torque should be torque of 2. And now, oops. Let's put torque of 1. We worry about the signs later on, right? Plus torque of W. Let's first worry about put and then like that. Torque of, let's start with torque of 1. Torque of 1, torque of 2, from the left to the right. Okay. So here we go. We do not know F1. We do not know F2. So because we have two unknowns, this single equation cannot solve the problem for F1 and F2. We need a second equation. Okay? Two unknowns, we need at least two equations. And the two equations must be independent of each other. So in order to find the F1 and F2, we are going to need this equation right here. Now let's take a look. Torque of 1 is counterclockwise, right? So we can explicitly state that this torque is going to be positive. And I'm going to emphasize that by putting those two bars around the torque, right? Now, let's look at the torque of the weight first, right? Torque of the weight is clockwise, where I'm taking this point as being the point of rotation. You can choose whatever point you want, okay? But you are better off in choosing a point where a force, one of the forces is applied to make it easier for you to solve this problem. This torque here is going to be negative, right? So I'm going to emphasize that this torque is negative by putting it within those two bars, okay? And now we have to worry about this guy here. Okay? We have to worry about this guy here. And because the point of rotation is this one right here, the axis of rotation is this one right here, and the force is applied exactly at the axis of rotation, the torque of this force is going to be 0. Make sense? Okay? That's the advantage of choosing the point of rotation at one of the points where a force is applied. I could have chosen a point of rotation right in here and take the torque with respect to this point. I could have chosen a point of rotation right here and take the torque at this point. In this case, tau 1 was going to be 0, not tau 2. But I chose this one here. Either way, you get the same result. Okay, so let's continue with the solution. The torque of 1, here you go. I'm going to illustrate that for you in the second drawing. Okay, and here you go. That's the vector of the vector position of the point of application of the force with respect to this point in the board. Okay? I'll call that R1. R1. Okay? And the other one is the vector of position, the vector position of the point application of the other force. I'll call that the vector R2. No, RW. I'll call that RW to remain consistent with the notation, right? And I'm going to put it in different colors so we can relate them by the colors more easily, right? This one is going to be, I'm going to put this one red as well. The W is going to be displayed as a red color, bold-faced. This guy, I'll make it, let's see, blue, like that, right? And blue, yeah. Notice that this vector here is perpendicular to this other vector, right? The sign, we already determined the sign. Consequently, what we are going to have here is R1 times F1. We don't need the 0 anymore. This one is going to be R W times W. Okay. Let's see what we do not know. We do not know this guy. I'm going to put in bold-face. Everything else we know, right? R1 is going to be the distance of the bolt to the fulcrum, 1.4 meters. Okay. And here we go, where R1 is 1.4 meters and RW is what? 3.9 minus 1.4. 3.9 is 2.5. RW is 2.5 meters. W and W is 520, right? 120 newtons. I'm not going to solve numerically. I'll leave you for you to double check that at home. Okay, I'm going to just put it. Okay, now I can solve for F1 here. Do you see that? I can solve for F1 here because I eliminated the unknown, right? When I eliminate the unknown, one of the unknowns, we can use just a single equation to solve for the other unknown. Next, ratio here, like that. That's F1. And now that we determine F1, we can determine F2, right? F1 goes right in here. I eliminated F1, that's what I did. And F2 becomes something like that. Okay, so we are done solving this problem. Okay. Now I can't do more than that, right? Just simplify here. Put W in evidence. Let's see here, put that. And we have a number 1 right here. Okay, example of, this is an example of equilibrium. And 43, let's go talk about Newton's second law of rotational motion now. 9.4, let's go there. Here you go. 9.4. What you have to know about center of gravity and center of mass, right? Center of gravity and center of mass is that their position, for the sake of this course, right? For the sake of this course, the position of the center of gravity and the position of the center of mass coincides with the geometrical center of the rigid body. And that's what I did there. Okay. Well, I didn't use that here in this solution, right? But if this board had a mass that were not negligible, it means that you had a weight being applied exactly at its center of mass that, in this case, coincide with the geometrical center of the rigid body. Okay. Now let's talk about Newton's second law of rotation. 1045. Let's go a little bit more, right? I'm in a hurry here to cover as much as I can of this chapter, so we're not left behind. What if the rigid body is not in static equilibrium? Then you must apply Newton's second law of rotational motion, okay? Just like we did for point particles. Okay, and how does the second law applies to rotational motion, right? To find out Newton's second law of rotational motion, we first apply to a point particle undergoing rotation. Okay, so we have this rigid body that's made up of several point particles. But first, let's consider just one mass moving in the horizontal with respect to the vertical axis. Okay, would be something like, let's see here. Let's think is this one right here, okay? You're gonna need here you go. So I'm gonna subtract this guy here. I'm going to subtract this one as well. Like that, here you go. Mass M, and length A. I'm gonna make it a little bit shorter. Grid line, yeah. So let's see, it's gonna fit. Let's make it a little bit smaller here. Yeah, let's see. Like that. I want to increase the size. Looks like I'll have to make it smaller. Let's see. Send to back. Let's see. 1, 2, 3, 4, 5. 1, 2. Yeah, I'm gonna make it shorter. Otherwise, it's not gonna fit here. 1, 2, 3, 4. Wait a minute. I wanna make it right in here. Yeah. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, it looks like we can make it. Here you go. A little bit to the left. Stretch a little bit to the right. 1, 2, 3, 4. Okay. So here you go. A little bit more to the left. And right. That's and I'm gonna dash the thing just to give the impression that this object is rotating about this axis here. So we need yeah, here you go. And the rotation, the radius of rotation is this one, A. I'll bring this A to the front. Yeah. So let's say, suppose that we have, right, this object rotating. We start with just one mass, and then we expand it to the other, to the case of a rigid body. Bring to the front. Yeah. Oh, no, you don't want to bring to the front. Yeah, you want to bring to the front, but you want to do something else. No fill. Okay. Now we got it. Okay. So on the top of that, we're going to assume that this object is subjected to a tangential force in order to apply Newton's, right, second law. We must have a net force there. If this one here is m, the other one there at the top is going to be a tangential force. And don't forget, this is a rigid body. It doesn't stretch, it doesn't compress, right? So it's not going to move away from the circle, right? It because this is a rigid body, even though it's made up of a single point, this axis of rotation is not going to change at all. Okay, so here you go. And we will be able to derive a very interesting formula, okay? And I will consider that this guy has a mass lowercase m, like that. Let's see, I'm gonna put R. Let's put R instead of A. Radius. So applying Newton's second law to this specific case, let's like that. Applying Newton's second law to this specific case, we get, okay, tangential force must be equal to the mass times the acceleration, the tangential acceleration, okay? And then we look at the torque that's being applied to this point particle. Okay? Look at the torque that's being applied. The torque applied to this point particle is going to be what? The tangential force times the radius, right? The point of application of the force, the distance of the point of application of the force with respect to the point of rotation, which is the force times radius. So a point particle can be subjected to a torque as well, not just a rigid body. Okay? But there is more. There's something else. Very interesting. Here you go. We can apply Newton's second law. And don't forget, this tangential force is the net force applied to this object. We can here write, right, the tangential force as mass times acceleration. And on the top of that, we can go ahead and here write my tangential acceleration in terms of the angular acceleration. Remember the angular acceleration that you saw before? It's going to be alpha times r. See that? Let me put those two together, right? Which can be simplified to m alpha r squared. And I'm going to commute this guy with this one right in here. And look what an interesting format that we get. And don't forget this, I'm going to put here net force as well, okay? So everything is very clear to you. The tangential force is the only force that's involved here. And here too, I'm going to write down net torque. Remember, right? Second law of motion is about the net force. If the second law of motion is about the net force, the second law of motion for a rigid body must be written down in terms of the net torque as well, right? So I'm going to copy and paste it here, and look what an interesting format for the equation that we have. Okay, we have something here, which I call mr squared, multiplied by an angular acceleration. Okay, multiplied by angular acceleration. Compare that with this one here, with Newton's second law. Net force is mass, or a parameter related to the inertia of the object, multiplied by an acceleration, linear acceleration. Here we have something else, right? We have an angular acceleration and another parameter that we call the moment of inertia, or the angular mass of the rigid body, okay? The term, here, let's write it down. The term mr squared in the above equation, mr squared in the above equation can be interpreted as the angular mass of a rigid body, also known as the moment of inertia. If mass is a measure of the inertia of a point particle, comma, the moment of inertia is a measure of the inertia of a rigid body. Even though we did just for a point particle, this whole thing can be expanded for a rigid body as well, okay? And how do you do that? Let me show how you do that. Okay, I'm going to write that down here, and and the rigid and the moment of inertia, we usually write that as being I. Okay, and that's the moment of inertia for a point particle. A point particle. Moment of inertia for multiple point particles, what that would be. Okay, the moment of inertia for multiple point particles would be a summation. Yeah, there you go. Like that. And now, remember I said it has to be a summation, right? So I gotta put the summation right in here. Let's say I don't need the parentheses. Okay. Suppose that we have n point particles. We sum from particle 1 to particle n. Okay. So spelling it out in terms, plus m2 r2 square plus 1, 2, 3 plus m n m n r n, yeah, like that. So that's in shorthand, we write like that. That's what we get for multiple point particles. And now we can write down our equation side by side. Moment of net torque is moment of inertia I. Net force is linear inertia of a particle, which is the mass, times the acceleration. Okay? Side by side. We can here, we can go ahead and here write that in terms of that expression that you saw. You go, and I'm gonna put that in between parentheses, so there is no doubt about that, right? Okay. What time is that? 10:59. And okay, so I guess we can have a break here for 15 minutes. And when we come back, we do a quick review, right, for the exam. Break from 11 a.m. to 11:15 a.m. Do you have any questions? Am I missing anything here? Doesn't look like, right? So I see you in 15 minutes. Stop sharing. I'm back here. I'm sharing the screen. And let's take a look at the chapters for the exam, for the third exam. 5, 6, and 7, right? Let's go back here to the syllabus. Yep. 5, 6, and 7. Chapter 5 is uniform circular motion. Chapter 6 is work and energy. Chapter 7 is linear momentum. And let's copy and paste all these chapters that we have for the exam. Review. Review for the third exam chapters 5, 6, and 7. Chapter 5, uniform circular motion. Chapter 6, work and energy. Chapter 7, linear momentum. conservation of linear moment. And what I want to do, I want to pick up all those sections of that chapter. Let's see. See if you have it here. No. Okay, that's the one. Oh, don't forget labs 4 and 5 too, right? 5, 6, and 7. All the way down. Here you go. Uniform circular motion. Let's what the equations that you have to know about uniform circular motion. Circular motion. Well, centripetal acceleration. Well, but before, what's the definition of uniform circular motion, right? Constant speed, constant radius, right? That's what you have. And let's talk about the equations of motion, right? The equations of motion for uniform circular motion. See, for some reason, okay. Equations of motion. Then we talk about the centripetal acceleration. Equations of motion. Here you go. In this case, we can start with the x and y. X and y equal. Here is x. Radius of the circle, cosine, oops, of the angle theta. All you have to do is to illustrate that like we did before. And let's get the illustrations here. Here you go. Uniform circular motion. X-axis, y-axis, right? Origin of the x-y axis. Here the path of the object, of the point particle. Is a circle of radius r, lowercase r. Let's use lowercase r. The mass is a given point there in this path, and we have this vector position r. The vector position has a x component. Oh, let's see here. The vector position has this unit vector that you see here. You have a velocity vector that's tangent to the path. And because it's constant speed, it means that there is no tangential force applied to this point particle. For this reason, the only force is going to be towards the center. And because we have just a force towards the center, we are going to have an acceleration that's going to be towards the center only, the so-called centripetal acceleration. We can locate this particle in terms of angle theta. And it's going to have an x coordinate that's going to be equal to r cosine of theta. And that's what I was writing there. R cosine of theta. Oh, let's use lowercase r, right? Uniform circular motion, circle of radius r, right? Constant speed, constant radius. Equation of motion is going to be like that. The y is going to be not cosine, but it's going to be sine. Okay. And this angle theta increases linearly with time, right? Is going to be what? Vt divided by r, right? The angle theta is going to be delta S over r. Delta S is going to be Vt. Constant speed V, constant radius r, like that. And it's the same thing that we get for this guy. Vt over r. The velocity is going to have a negative x component. Let's see how I'm going to do that. Constant speed. Let's put v naught here. Oh, no. Wait a minute. Yeah, constant speed v naught. Yeah, let's do this one. Here, we should write down the x component of the velocity is going to have a negative component, right? V naught, and what goes here in theta is not going to be cosine, it's going to be sine, and the argument is going to be exactly the same one. Okay? And all you have to do is to break down the velocity components that you saw that, right? Let's see here. I think I have, here you go. Here's the velocity component. Okay, here's the velocity component, 90 degrees minus theta. Right? What was cosine becomes sine. Cosine of 90 minus theta becomes sine, right? And you can see that at this position, the component of the x component of the velocity is negative. And we have something similar for the Vy. The only difference means that here you have a positive value, and here you have a cosine. See that? X cosine, Vx sine, y sine, Vy cosine. And we finally have the x component. Don't forget that the acceleration component must be the acceleration vector, centripetal acceleration vector points in a direction opposite to that of the position vector, right? So you're going to have, yes, something here times cosine of theta. Cosine of theta, we already know that's going to be Vt over r. Okay, this is going to be my acceleration vector, my Cp, right? Cp here, centripetal acceleration vector. And here too, Cp acceleration vector. But because it points in the opposite direction of the position vector, we must have a negative sign in both of the components. Okay? Cosine, sine, cosine, sine, cosine, sine. Minus here, only one term has a negative, and then this term here has two negative terms. And the centripetal acceleration, we derived that it's going to be V naught square over R, right? Here you go. V naught square over R. Oh, I don't want that. I want to repeat it. Any questions? Okay, so here you go. Velocity, okay. And here's the derivation of the centripetal acceleration, the derivation in terms of similar triangles. You should memorize, it's fine, the derivation is fine. If you don't memorize, also fine, but at least you have to memorize the final result, which is V squared over R. Okay, here's the case, an example of of an airplane, a model airplane, right? That's undergoing uniform circular motion. You have to break down, to identify, not to break it down, but to identify the forces acting to the airplane. You have the lift and the weight plus the tension in the string. And we solve that problem, right? Here's the case of the car in a circular track. Okay, and we want to know the maximum velocity that the car can go through this curve to negotiate the curve safely. Okay, so let's write that down here. Okay, for a car negotiating a curve, negotiating, right? A curve, circular curve safely, we have the negotiating a flat curve, right? A flat circular curve safely, we have the following forces, weight, normal, oh gosh, my typing is terrible, and static friction, which is the centripetal force. Just a reminder, right? Weight, I'm gonna put one by one here, weight, normal, and the final here, static friction, which is the centripetal force. And that's the really trick here. The static friction is the centripetal force. Okay. Apply Newton's second law and find the maximum speed it can go through the curve safely. That's one of the examples that we did. Here you go. Here you go. Here are the forces, normal weight and the centripetal force. We didn't know right from the bat. We didn't know what was the centripetal force, and later on, analyzing carefully, we figure out the centripetal force must be the static force of friction. Because if there was no static force of friction, the car just would move in a straight line instead of undergoing uniform circular motion. Okay, car in a banked curve. Here you go, car, for a car in a banked curve, we have the following forces. Okay, we have the car in a banked curve over a frictionless surface. Okay, we have the following force. This banked curve of angle theta. Angle theta. Weight and normal. That's all you have. Weight and normal. Okay. Because of the banked curve, the horizontal component of the normal acts as the centripetal force. Someone else is trying to get in. See, Ruth. Okay, Ruth, I'm giving attendance here. Okay,
Hi, Professor, I'm here.
Okay, who is that? Ruth, right?
Yes.
Okay, good. Audrey left, Rod. Okay, Audrey left. So 11:30, you gotta finish that so you can do the rest. In the case of the bank curve, right? Here you go. car will slide toward the center of the curve if it doesn't do anything. Icy road, no friction, right? And here you go. The forces are going to be here. Here you go. See that? The horizontal component of the normal. We have only two forces, but the horizontal component of the normal ensures that the car can can go in a circular path. Okay? If we add friction, okay? If we add friction, then we have to add another force there. For a car in a banked curve of angle theta over a surface that has friction, now we have the following forces. Okay, weight, normal, and static friction. Okay, in this case, now I'm going to write that down here. In this specific and right? And in this specific case, both the normal, the horizontal component of the normal component of the normal and the horizontal components of the normal and static friction adds or subtract, right? Adds up or subtract, add or subtract to adds up to the let's put adds up to the centripetal force like that. Okay. Did I illustrate that? Let's see. No, I didn't. I didn't illustrate that. But you can think about the force of static friction here, either downhill or uphill, depending on the velocity of the car, okay? And we also have problems of satellites in circular orbits, okay? Satellites in circular orbits. In circular orbit, okay? The centripetal force is the force of gravity. Okay, and so let's see, let's hear centripetal force. Okay, so here you go. It's going to be like that. G m over r squared. That's going to be the centripetal force. Right? And you put on the right side, you put v squared over r, like that. To solve your problem. What else? Okay, let's see. Yeah, the same case for the artificial gravity. Artificial gravity. Artificial gravity in space. Put a cylindrical structure to rotate. And you will create artificial gravity, right? What else? mv squared over r is going to be equal to the normal. Okay, it's going to be equal to the normal. mv squared to the okay, let's see this one here. yeah, we're done with this chapter. Let's go to the next one. Work. Okay. Okay, so here you go. In order to define work, we need the x and y axis. We put the mass in the x axis and apply a force. And then we come up with this useful definition that's called work done by a force. The work done by a force is going to be the force multiplied by the displacement multiplied by the cosine of the angle between the displacement vector and the force vector. Okay? So let's go. Definition of work. Chapter 6. Work and energy. Definition of work. Work is going to be F times delta x times cosine of the angle between the vector and displacement force. The vector displacement and the force and the vector force. Theta, like that. Okay? Definition of work. And here I'm going to specify that the work done by a given force F. Expanding this definition to the net force, we get the following. We get the work kinetic energy theorem. Okay? So I'm gonna put like that. Net, right? Work done by the net force is going to be given by what? Going to be given by the final kinetic energy minus the initial kinetic energy. Or, if you want to simplify the notation, delta KE. Put that between parentheses. Okay. And this thing can be here written in another different way, considering now two types of forces, conservative force and non-conservative force. Non-conservative force. We have the work done by the net force is work done by the conservative plus work done by the non-conservative is going to be equal to the difference in kinetic energy. But we also saw that, we also defined that conservative forces have a so-called potential energy, right? Let's write down P. Did I use P there in the back? Let's assume that I use P in the back, right? So the above, so the definition of the potential energy now is going to be what? It's not so-called potential energy, but the difference, okay? In potential energy, delta PE. Delta PE. Delta PE. Okay, so the difference in potential energy, which by the way is equal to the final potential energy minus the initial potential energy, is equal to minus the work done by the conservative force. So there's a very important difference between those two forces, right? That we discussed at length before. 1142. Okay, and let's see here. We can rewrite this equation now in terms of the difference in potential energy, final potential. Don't forget this, work of the conservative forces minus delta PE, like that. Okay, and then we have the terms of the non-conservative here. And now I'm going to rewrite those two terms here, just like a final kinetic energy, just to simplify, right? Simplify the notation. Kinetic energy, initial kinetic energy. Like that. When we do that, we get minus final potential energy plus initial potential energy plus the work of the non-conservative forces. And I erase this guy here, don't need that anymore. And now we can rearrange this equation to make it look at more intuitive. We pass the final potential energy to the left, change the sign. We pass the initial kinetic energy to the left, change the sign. And now we start to have something close to what we call the conservation of energy. And this conservation of energy we call it mechanical, the potential versus the kinetic energy, we call it the mechanical energy. Okay, mechanical energy on the left, initial mechanical energy on the left side, final mechanical energy on the right side. Okay, if if there are only conservative forces, then the above equation becomes a special case. Okay. Examples, here go. Variable forces. Oh, by the way, potential energy, special types of potential energy. Special types of potential energy. We have to memorize. Okay. Nearby the surface of the Earth. Okay. Potential energy is equal to mgy. Okay. Far away from the Earth, far away from the Earth's surface. Okay. Potential energy becomes what? Minus G big M over little r. It's independent on the mass of the object. Okay, far away. Now, elastic potential energy. Elastic potential energy is going to be, I'm gonna put it elastic here, is going to be half k x squared, where k is the spring constant, right? And x is the displacement from the position of equilibrium. 1147. Am I forgetting anything else here? Let's see here. Satellite, yeah, I did all of that, right? Work done by constant force, work done by kinetic energy theorem, gravitational potential energy, conservative and versus non-conservative forces, conservation of mechanical energy. Okay. The only thing that's left here is the power, right? Work done by variable force, in the case of elastic force, power. Power. The definition of power is the speed at which you use up energy. Delta work over delta t. Delta t, which, by the way, ends up being force times velocity. Okay? So that's what we have for chapter 6. And then we have momentum. Linear momentum. Momentum. Definition of linear momentum is linear momentum is a vector like that. So it's mass times velocity like that. Okay. If the net force applied to our system, and you can define the system whatever way you want, and you may define the system in whatever way you want. If the net force applied to our system is 0, then we have conservation of linear momentum. Okay, and conservation of linear momentum means final momentum is equal to initial momentum, right? Three important cases of conservation of linear momentum. The simplest of all of them is inelastic collisions. Okay, in an inelastic collision, final velocity of object 1 is equal to final velocity of object 2. Like that. Right? And we have conservation of linear momentum. Here you go. M1. Let's see. Times B naught 1 plus M2. That's the most generic equation that you're going to see, right? V. Oh, and let's put also our vector here, right? To make it even more generic. Vector. And then all I have to do is to change this script from initial to final. Initial to final. Like that. Oh, and by the way, because final of 1 is equal to final of 2, we can write that down as being we can put the final velocity, right, in evidence. Instead of writing in terms of final of 2, let's write in terms of final of 1 in elastic collision. Okay, explosions. Initial velocity of 1 is equal to initial velocity of 2, right? It's initial, it's not final. And now we have something like that. Conservation of linear momentum. Let's put everything in terms of initial velocity, right? That's what we have. If you know the amount of internal energy stored before the explosion, you can solve this problem. You can completely solve this problem. Totally elastic, let's see, 7 minutes to go. Totally elastic collision, conservation of momentum, and conservation of energy. Okay, it's going to be like that. If the collision occurs in a flat terrain, right, then there is no change in potential energy, right? There's no change in potential energy, right? So what we're going to have, if there's no change in potential energy, the potential energy on the left side of the equation, right? Here, initial and potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. You don't need a subscript, right? If there is no change in potential energy, what does it mean? It means that U naught is equal to U, right? Like that. And the conservation of mechanical energy becomes just conservation of kinetic energy. That's why I didn't take into account the potential energy, because most of the collisions that we use occurs always in the same height, right? If the collision occurs in the flat terrain, then there's no change in potential energy. And we have the following two equations. Okay. Initial kinetic energy is equal to final kinetic energy, and the final linear momentum is equal to initial linear momentum. And 1155. Yep. And then we have collisions in 2 dimensions too, right? And let's see what else. We have 4 more minutes to go, right? 4 more minutes to go. So we have that special case 2D totally elastic collision between objects of same mass, right? One mass, one object, initially at rest. Okay, so what do you get? We get that interesting result that you saw Here you go. Initial velocity vector of 1 is equal to final velocity vector of 1 plus final velocity vector of 2. And then we have, what time is that? 11:57. Okay, we're in good shape here. What else we have? We have something like that. Oops. That what the equation for conservation of momentum tells you, right? This is the equation for conservation of momentum that we simplify it. We cancel the masses. And what you're going to see here is the conservation for kinetic energy. Initial velocity square is of 1 is equal to final velocity square of 1 plus final velocity square. We gotta take out this vector from here. Otherwise, it's not gonna be complete. Yeah, let me take it out. Let's take it out. We're almost ending here. Okay, good. Well, so to the totally elastic equilibrium between object of same mass, one object initially at rest, okay? And that's what we have. 2 more minutes to go. Do you have any questions? I didn't prepare the exam yet, but I'll be preparing it before the exam, right? And if you don't have any questions, I will see you Wednesday. Okay? Thank you for being here.
Thank you, Professor.
Um, let's see what I have to do. Stop recording.